So today we will be talking about the feature engineering. So let's see what is the agenda for the same. So today we'll talk about what is feature engineering, why feature engineering is required, what are the different types of feature engineering, and today our entire session is based on missing and the junk values and how you can handle. There are multiple techniques to handle the missing values and the junk values. Along with that, we will have a Python code walkthrough on it. So before starting, I would like to know what do you understand by feature engineering? Any idea? Any one of them? You can put your answers in QA section. Okay. So you do. So let's talk what is feature engineering. So basically, feature engineering is a stage of a data science project where we try to reconstruct the features. When we say reconstruct or re-engineer the features, that means something is available already with us and we will make it, we will do the reconstruction of the data. Okay. But it will be not manipulation of data. Basically, it will be applying the manipulation on the data. Okay, fine. Okay, so before starting, let's think when a data scientist work on any data science project, how much time he spends. Okay, if you can see the blue portion, so it comes into cleaning and organizing. So cleaning and organizing is the feature engineering stage. Sometimes people also call feature engineering as data pre-processing also. Okay, after that we spend most of the time into data gathering, right? And then we have certain other things which are part of the data science project. So if you can see, most of the time is spent on the cleaning and organizing the data. Why it is so? Because if the data is cleaned, if data is tidy, the other stages falls into their own places. That means the ultimate goal of a data scientist is his model should perform very well on the unseen data. So that is the ultimate target for a data scientist.
Also, in this stage, team, what you guys understand is if you see here, it says cleaning and organizing. You'll also be in a real scenario where data is not clean and data is very inconsistent. You will be working largely with the business side of the process. So basically, you'll be understanding what these features means. Not always, as data scientists, we immediately correlate or resonate with a particular feature. We don't understand. And when we work on domains that's not from what we belong, which are not common. For example, let's say if you get into a medical space, if you get into something with, any of those biomedical spaces, will not understand what these features mean. There's absolutely no way. And as data scientists, we are not meant to know that either. However, for us to build a machine learning model or a prediction or a data analysis, we need to understand what these features mean, at least at a high level. And at this stage, in a real scenario, you'll be working a lot with business, trying to understand how to impute missing values, because it's not always going by one approach. I don't know. I think missing values is taken today or in the next session. I'm not sure, but yeah, you'll be doing a lot of these things with. I think missing values is done. So you'll be working largely with business teams to understand these features. And when you see here, that's the reason why the time taken to do this is also significantly very high. It's majority of the time actually goes in cleaning, organizing, and understanding the data. When that is in place, anything which we do beyond afterwards, in terms of our doing our predictive analytics, running our predictions, doing our what do you say, our visualization, our dashboards, everything makes sense when this basic foundation is clear. So there's this misconception that, hey, data scientists just run algorithms. No, if that was the case, we would not need human beings, right? We could automate these processes. So a lot of time goes there. This is very important. Even these are one of the things that frequently gets asked in interviews as well, because it's data science is not just about running algorithms. There are a lot of things which goes behind that, and This graph clearly says majority of the work goes in this activity itself. So that's what I wanted to weigh in. Shubhangi, you can proceed.
Yes, so Deepak, as mentioned, the cleaning and the organizing of data becomes super important. As we know, the data scientist job is not to build the algorithms. They have to work parallelly with the business team. They have to work parallelly with the domain. They have to work engineering side. So many things are there. Okay. So somebody said tidy data sets are easy to manipulate, model, and visualize, and have a specific structure. Each variable is a column, each observation is a row, and each type of observational unit is a table. So basically, a clean data set gives us more, more power, more strength to create a better model. Okay. So that is why the cleaning of data is super important. So as I mentioned, feature engineering is a stage, okay, where we work with the features in multiple ways so that end results of model are promising. Okay. Feature engineering also covers the aspect of data pre-processing. Okay, so most of the time people are confused. Feature engineering and data pre-processing both are different. If you really think through, feature engineering basically correcting the features, okay, or engineering with the features. Data pre-processing, features have its observation, as if you remember in the last slide we have seen, right? Either way, both are same stage only. So usually I prefer calling feature engineering and data pre-processing both. Okay, so in most of the interviews also people ask questions, what is feature engineering and what is data pre-processing? Okay, so ideally you can give the example, both are same. Okay, so the ultimate aim of feature engineering is to get the clean and meaningful data, so that whatever application we develop, it should have valid, it should be valid. Okay, so this is what a feature engineering means. So feature engineering is required to handle data corruption. Now let's talk about, this was all about the feature engineering, but what we try to do in a feature engineering, let's try to see. Here we handle data corruption because our algorithms, if they learn the corrupted data, that means the model is also corrupted, and always it will do the prediction on the corruption data. That is not fair, right? So that is why feature engineering is required. Okay, so it's not only about handling the missing values or the corruption data or the junk values, but we can create features out of the given features also. And apart from that, we transform the data, right? Transforming the data, basically what sometimes it happens most of the time, some values don't work as is. We need to take some kind of log, some time of exponential of that values, and on that value model performs really good. That means our model is able to find the pattern in the log taken data instead of the original data. So transformations become also important. Then feature extraction, we can extract feature, we can create new features. Okay, so this is what we try to do in the feature engineering step. So let's drill down into the types of feature engineering. So in the last slide, we have seen about the broader categories, right? Now let's see on the drill of the feature engineering. So the first and the most important aspect of data is that the data should not have junk values. It should not have missing values. So whenever we start working on any data science project, the first approach is to handle the missing and the junk values. Okay, when I say missing values, that means the value got missed while taking the observation. Okay, and junk value means, let's say, some question mark, some kind of junk values are coming. Okay, it happens if you let's say we are collecting the data in the form of Google form, right? People usually they will put some random digits, they will randomly put some of the data which is not required. right? So what we as a data scientist do, we convert them into the missing value, basically the null, and then we apply the techniques over there. Okay, so the first and the most important part of feature engineering is handling the missing value. Right. After that, what we do, we go and convert the categorical data. Okay, so in most of our data, we have categorical features. Okay, so categorical features must be handled because our models are built to understand machine language, that is 0 and 1. They cannot understand the string data. So conversion is super important. Okay, then we have a outliers. The major problem with any kind of model is the outliers. Okay, if your data has outliers, the algorithms which uses distance, okay, which uses gradient descent to calculate the errors, right, it becomes difficult for them to do the prediction on the outlier data set. Okay, similarly, the same case goes with the scaling also. Okay, if the magnitude of features, different features are varying a lot, that time also the algorithms thinks the feature with more magnitude is more important as compared to other. But it can happen, both variables are super important for the model creation. So in this way, we leave the less important data, basically model leave the less important data, and it goes with the data with the higher magnitude, right? So that time we have to scale the data, and then we take transformations. So as I told you, transformation, I told you just now, like if we take log of the same value, model is able to find pattern in that log, but it's not able to find the pattern in the raw data. So transformations are that technique. Okay, there are multiple transformations. Okay, then we have binding technique, right? Sometimes what happens, some continuous variables cannot give, we cannot understand the pattern in that particular variable, okay, with respect to a target. So what we do usually, we create bins in the data, bins in nothing but the range. Okay, so just the way we create histograms, right? So we can create bins in the data, and on that bin we can train the model. Let's say I have collected the age. Okay, so instead of passing entire single age, I can pass the bin data, like from 0 to 20, I'll call the people as a kid category. Okay, from 20 to 40 or 45, 50, I'll call them as a adult, and then after that I can call them as a senior citizen. Okay, so these are the binding technique. Okay, this also performs really well when we do the feature engineering. Okay, and this is not the last. Okay, feature engineering depends upon the type of data you have received, but these are the most common thing which we usually do it. Okay, feature splitting means, let's say in a single feature we have two information, okay, country and the city name. So we can split the feature and we can create a new feature out of it. So these are the ways in which feature engineering are done. So feature engineering technique depends on how much, what kind of data you have received. Okay, but yeah, these are the major problems which will be associated with our data. Okay, I hope you guys have heard on this part. Okay, fine. So the today's webinar is totally on handling the missing values and the junk values. So Vaishaki will be taking over us to the types of missing values and then the methods to handle them. Okay. So as I mentioned, the most common problem associated with the data is the missing, right? Okay. So now over to you, Vaishaki. You can go ahead and start with the presentation for the missing values.
Thank you so much, Shubhangi, and thank you, Deepak. First of all, good morning to one and all. I hope you are doing well. As Shubhangi has rightly mentioned, the different techniques of feature engineering and why feature engineering is important. So today's session, we will be mostly focusing on the missing value imputation techniques. Shubhangi, can you please allow me to share the screen?
Go ahead, Vaishakhi.
Right. So first, let's discuss today's agenda before we start with the session. So today in missing value imputation, we will first be discussing what it is called. So imputation or missing value imputation is the act of replacing whatever the missing data we have with some statistical estimates of it. And the goal of our imputation technique is always to produce a very clean or complete data set that we can use to train any machine learning technique. In this missing value imputation today, we'll mostly cover multiple imputation techniques that we can apply for, namely numerical data. So the type of data it depends upon. In numerical data, then in categorical data, and some of them that we can apply to both of them. Okay. For numerical data, we'll discuss mean and median imputation. And the second one is that we'll discuss is if we are imputing the missing value with some arbitrary value. When it comes to categorical data, we'll be discussing something about mode imputation, or this can also be called as frequent category imputation. And the second technique for categorical data that we'll discuss is called as, again, arbitrary value. When it comes to arbitrary value, we'll be replacing them with a category called as missing. So basically, we will be creating another category of all the missing data itself. And techniques that we can apply to both numerical and categorical, in this, we'll discuss something called as CCA, which is also called as complete case analysis. In this, we will be removing all the rows which has the missing values. And the other one that we have is, again, the arbitrary value imputations, or adding a missing indicator. That was, again, something similar that we had in the categorical one as well. Here we will learn how to implement these techniques in the libraries Pandas, NumPy, and scikit-learn. And so these are the three main objectives for this session. So the first one is to understand that there are multiple ways in which we can impute missing data. So I would introduce you to the very many techniques that we can use. The second agenda is to also understand the impact of these techniques on the variable distribution. Also, how these variables will interact with other variables. So we will compare the variable distribution pre-imputation with post-imputation. And we will see how it affects not just the distribution, but how the interaction of this particular variable is there with other variables. Let's say with target variables or other independent variables also. And also we will understand how these techniques may affect the performance of our machine learning model. So let's say there are some models that rely on distributions, that they should be normal, let's say linear regression. So we will understand how the impact of this missing value imputation technique can lead to performance of different machine learning algorithms. And the third objective will be to learn how to implement these techniques using the Python code. So I'll be sharing the codes for it as well. We will have a walkthrough of the codes and we will understand how the impact is. And we will also understand its impact in the pre and post stages. But before proceeding ahead with the same, we will have to understand what are exactly these missing values. What are the sources of it? What are the reasons that we have missing value in the data? So first of all, missing data is nothing but the absence of values in certain observation of a variable. And missing data in any data set is an unavoidable problem in most data sources. and it can have a very significant impact on the conclusions of the algorithms. So as I stated, why is the data missing? What are the reasons that the data can be missing? So basically the source of any missing data can vary. Let's say sometimes the value was forgotten, or it was lost, or it was not stored properly, right? Or the value does not exist only. Or let's say the value of that particular feature was dependent on multiple other variables, and sometimes we were not able to fetch the data of any of those variables, and hence there was a missing value placed. Or sometimes the value can't be known, or it cannot be identified. So suppose I want to give you a real life example. A person may choose not to complete all the fields in the form. And if they are not mandatory, they may want to skip it. Let's say you might have come across feedbacks for lots of applications that you newly installed and you were using. And sometimes the fields that were not mandatory, the most common one is any suggestions. So you will always prefer to skip them. So in those cases, certainly the data set might have a missing value that would introduce a missing data over there. Sometimes people do not want to disclose some information, for example, income. In case of women, we say age, or they do not know the answers to the questions being asked. Sometimes the value for a certain variable, it does not exist only. For example, if the variable, let's say the total debt as percentage of the income, it is very common in financial data, but if the person has no income, then the total percentage of 0 does not exist, because we have income in the denominator in order to count the total debt. So if the person does not have an income, we cannot put 0 and we cannot get an unidentified value. In that place, they can get replaced by a missing value. So it is very important to understand why data is missing, or in other words, the mechanism of this missing data. What is the mechanism? What is the reason why the missing data is there? We may process the missing information differently depending on this mechanism. And furthermore, identifying the source of this data, it allows us to also understand which technique would be most feasible for us to perform best in the future algorithm implementations. It also allows us to take different steps how to regulate that source and reduce the amount of missing data as the data collection progresses. So we'll understand the different types of mechanisms, different missing data mechanisms. The first one is missing MCAR, which is called as missing completely at random. So when the data is completely missing at random, the fact that the data are missing is independent of the observed and unobserved data. Or in other words, we can say there is no difference between participants with missing data and those with the complete data set. For example, some participants may have missing laboratory values. We are working on a healthcare domain data set. We have some missing data due to some missing values in laboratory, because a batch of samples was not processed improperly. It did not give us proper results. So in these instances, the missing data, it reduces the analyzable population of the study and the statistical power as well. The next missing data mechanism is missing at random. If the probability of any observation depends on the available information, that is, when the observation is missing at random. So this is a relationship between the likelihood of a value being missing and the observed data. For example, men are more likely to disclose their weight than women. So weight can be considered as a missing at random value. The weight information will be missing at random for the men and women who did not disclose their weight. But as men are more prone to disclose it, there will be more missing values for women, right? So in this example, we can say that missing data are no longer a random instance, but they are majorly depending upon the gender. Or we can say in case of income also. In case of income, men are more likely to not disclose their income as compared to women. Or women are more likely to disclose, or men are more likely to disclose their age as compared to women. So if we decide to proceed with the variable with missing values, in this case, if we say the weight or this, if we say the age, we might want to include the other variable as well, that is the gender, which controls the effect of the age variable for missing observations. The third mechanism is missing not at random. If there is a mechanism or a reason why data is missing, then that data is missing not at random. For example, if we are dealing with a data set of, or if we are trying to find out if a person is going through depression or not, let's say. So we have a survey of a lot of people, and in that depression survey, because of that depression, probably the people who are facing depression might not, they might not have filled the forms correctly. They might not want to fill out all the necessary columns because they are going through that mental problem. So if people fail to fill out a depression survey because of this depression, those data points would be missing not at random. So missing data occurs due to the depression. So depending on the mechanism by which missing value occur, we may choose different missing data imputation methods. So these are the main three mechanisms: missing completely at random, missing at random, and missing not at random. So after understanding this, we can proceed ahead with the data imputation techniques, missing value imputation techniques. The first one that we'll discuss is the complete case analysis that we can use for both numerical as well as categorical data. CCA, or complete case analysis. It also is called as list-wise deletion of cases, because here we are deleting the rows which possesses the missing values. Discarding all the observation where values of the variables are missing is called as complete case analysis. We analyze only those observations for which there is information in all of the variables in the data set. And it's a technique that is suitable for both categorical. This is suitable for categorical data as well as numerical data. So for example, we have gender, and we have something called as, this is a data set for, let's imagine that we have this data set which has 4 variables. Okay, one is gender, we have price, we have make or the brand of the engine, and we are actually at there, we will have lots of missing values. Suppose we have over here female, the price is somewhere around 100, the make of the car would be, let's take Ford, and then in this we have a missing value over here at gender, and let's take this as 90. This is also Ford, and here we have the male. So this is the user, that the person has either bought this car or they are willing to. Then we have something over here as Kia. So in this case, the observation that contains missing data will be removed entirely from the data set. So this row, if we take into consideration this one, we will completely eradicate the row from the data set. So complete case analysis, they make an assumption also on the data. You can apply this technique on the basis of the assumption that the data is missing at random. Okay. The advantages of this technique is that it is very simple. You just have to remove all the NaN values, or you can just remove all the columns with NaN values, and there is no data manipulation required. It also preserves the distribution of the variables. However, if there is missing data across multiple variables, or if the number of missing data is high, in that case, if you go for deletion of rows, so you can imagine if suppose gender has greater than 50% of the data missing. So if you'll go for complete case analysis in this case, you will see that the data set has 50% reduced because 50% of the rows will get deleted, right? So this is only applicable in cases where the percentage of missing data is less. We cannot go ahead with losing out informations. Also, some of the excluded observations could be informative for the target that we want to predict. But in this case, it will also create a biased data set. Suppose if we are removing this data, we are removing this row completely, there can be a possibility that these values of price and the make of the automobile is information in predicting the target. But if we are removing them, there is a possibility that we will get a biased data set. So finally, when using our model in production, the model will also not know how to handle this missing data because we didn't introduce any feature engineering technique, how to handle them. So whenever the model will come across the new data in production, if they have any missing values in it, the model will fail to understand the pattern or how to handle it. And in that case, there will be problems occurring. So which is to remove, whether to remove it or whether to keep it, model will not able to understand it. So what exactly we lose in complete case analysis? As a guideline, complete case analysis should be used only when the data is missing completely at random, and also when no more than 5% of the total data set. So we also have to make sure these are the assumptions. First, that when the data set is missing completely at random. And the second assumption is that the proportion, the percentage of missing data should be less than 5% of the total data set. So now let's look at the codes. We'll move ahead with the Python implementation now. So we are taking a data set called as house price prediction. This is readily available on Kaggle as well. And for this, we have imported the basic necessary libraries first. We have imported our data set using read_CSV. And we have explored this data set. If you see, there are lots of columns, both numerical and categorical observed. And there are lots of missing values in some of the features, namely Ali. If you scroll through, there are lots of features as well. Yeah, so these are only the top 5 rows, and let's understand what are the different features that contains the missing value next. So this code will provide us with the list of features that have missing values. So here this code, as we have mentioned, mean is greater than 0. So we are checking how many have how many have a percentage of missing values. So these are the features that have all the missing values in it. Next, we have checked the data type of these. So we can see that there are lots of categorical variables as well as numerical. Both contains missing values. And we have created a different data frame itself, where we have kept only the features having missing values separately. And this is how the data frame looks like. Now what next we want to do is we want to check the percentage of missing values that each category or each feature has. So this is the code that we have used, and we have come across with the variables. These are the variables and the percentage of missing values that they possess. So that is over here. Right. So there are some features, let's say pool QC, miss features, they have around 99% of the data is missing. So certainly if we will go ahead when applying CCA over these features, we will not be left out with any data, right? So we can skip the above around 6 of the features, let's say even lot frontage. we can apply CCA for all the features which has around 5% of missing values and below that. So we can take all these features, garage type, from garage type to electrical, and we can apply CCA on all of them. Okay. To identify that, we do not have to, this is the code that you have used. Instead of putting the mean of the null values less than 0, I've put it as less than 5%. So this will reflect all the categories that has either 5% or less than 5% of missing values. And then directly we are using drop NA because we want to remove the rows completely from it. So drop NA, we can use it, and we will, this is the data set that we have now after removing of the null values. So as I said that we will be comparing its effect on the distribution of the variable before imputations and after imputation. Well, here we are not imputing, we are just removing them. But let's also observe how the distribution has varied. So this is the histogram of one feature, which is great living area. I think this is for the living area in square feet. And we are comparing the histogram of this feature, great living area, before removing or before CCA and after CCA. The red color is before CCA and the blue color is after CCA. So if we see the distribution, they seem to be overlapping a lot. Okay. And we can see that we have only removed around 48 rows in total out of the 1400 rows, 1460 observation, I think we had, and we only removed around 48 of them. So I finally, I want to compare the distribution in this case, because I want to also show you that if the data was missing at random, the distribution of the variable, it should be preserved. And here, as I say that for the variable ground living area, we can see the distribution before and after the CCA of the variable is very similar. And this is the case for numerical data set. Even in case of basement fin SF1, in this case also we see the blue one is before the CCA and the red one is after, the red is before and blue is the after CCA. And we can see the distribution is quite preserved. Okay. So if the data set is missing at random and if the proportion is less than 5%, we can go ahead with CCA. Distribution has been preserved. Okay. These are examples for numerical data set CCA. We can also apply for categorical variables. For category variables, to understand whether the distribution is preserved, we can do frequency analysis in place of understanding the histogram. Instead of that, we can go for frequency analysis. So with this, here we can see this function I have used for it. With this function, I have calculated the percentage of observations per category in the original data set and then in the data set with complete case analysis. And we can see the example output of the variable for the basement quality. The basement quality example, okay, let me just. Just give me 2 minutes. So we will see the variable, because of the distribution of observations for the category, is roughly the same only. Even in case of categorical variables, we will see that the distribution will roughly be same. This is for ground living area, numerical. This is basement fin SF1. Yeah. So as you can see in the original data set, before CCA and after CCA, you can see this. The frequency distribution has not changed a bit. I mean, it has certainly changed, but not with huge indexes. So they have been preserved in case of categorical variable also. Okay, the distribution of houses in each of the categories is very similar in the original. and also in the case of CCA. And this is what we have expected from CCA also, if the data is missing at random and the percentage is less. So this is the first imputation technique that you can use for numerical as well as for categorical data. The next technique that we'll study is mean or median imputation. Mean median imputation consists in replacing all the missing values via the mean or the median value of the variable. And naturally, it is only applicable for numerical variables. So let me give you an example. Let's say that we have a variable price that contains value in many observation, and it has a lot of missing values as well. Let's say we have 100, 90, 50, 40, 20, 100, and then we have missing value, 60, 120, another missing value. These are the price feature. And it also contains these missing values and where the observations is not available. So in this case, we can impute these missing values with either the mean of the feature, which will be roughly somewhere around 86 or 0.66, something around that. Or we can impute it with the median. Median is the middlemost point. If we arrange this data set in ascending order, we sort it out first, and the middlemost point that we get is called as the median. So here we can impute it with either median as well. In this case, if we are doing mean imputation, what we do is we calculate the mean price for all these values, which we have found out is 86, and then we use the mean to replace. But as you can see here, if it was to replace by the median, we will be doing it with 90 value. But why should we use, or when should we use the mean, or when should we use median imputations? So mean we can use, or it is suggested to be used when the variable is normally distributed. When this variable is normally distributed, we can go for mean imputations. Either in case of normal distribution, we can also go for median imputation as well, because in a normally distributed variable, we observe that mean and median are almost the same only. But if in case we have a skewed data set, if we have distortions in the distribution, if we have a skewed data, in that case, we will observe that median is not, or median is slightly affected due to the skewness. It almost does not distort from its original position, but mean is very sensitive towards skewness. So if the variable is normally distributed, we can use any of the two imputation techniques. However, if the variable is skewed, mean tends to be sensitive. It is influenced by the values at the far end of the distribution, and therefore median becomes a better indication of the majority of the values. Mean and median imputation as a technique, it naturally also have some assumptions. The first assumption here again is that the missing data missing at random. This assumption is also applicable. So if this is the case, the missing observation most likely would look like the majority of the observations in the variable. But there are some limitations that we need to consider. The first one is that with mean or median imputation, if the data set has higher value of missing data, and if you are imputing them with the mean or median, the concentration of values within the mean range or in the middle of the distribution will get accumulated more. You will see that the data or the kurtosis of the data will rise. It will increase. It certainly will distort the regional distribution of the variable. It also distorts the regional variance of the variable, which is again the part of the distributions. And it also distorts the interaction with other variables. So let's say previously we will also see the covariance factor, how it is affecting the other variables. We will see that in the Jupyter file again. And also it depends on the percentage of missing values, certainly. So if we have a higher range of missing values, or if the higher the percentage of missing values we have, the higher will be the distortions of the distribution, higher will be the distortion in the regional variance, and also it will distort the interaction with variables accordingly. So however, in good practice, what people would rather do is they apply mean and median imputation, but this is done together with adding another indicator variable to capture other observation where missing data was missing. I'll explain. Let's say missing indicator is a implementing missing indicator technique that we'll cover later in this section only. But when we do these two techniques together, what happens? We are covering two angles. First is the data was missing completely at random. This will be captured by mean or the median imputation. And if data wasn't missing completely at random, then the data and the missing data or the missing category imputation has some predictive value. And it should also be captured by some indicator. So what we can do is we can use both the techniques together. Viable, both the methods are extremely straightforward to implement, and therefore they are on the top choice for most of the data science competitions as well. So next, we will take this forward to the Jupyter notebook and let's understand how this is done on data sets. And we'll also compare its influence on the variable distribution and the regional variance. So for this, we have used the Titanic dataset. Again, this dataset is readily available on lots of online resources. In this, we have only used three categories, three features: the age column, fair, and survive. These three we are going to analyze because these three have different percentage of missing values. This is how the data set with these three columns would look like. And this is the percentage of missing values in these three different features. So if you see age, it has around 20% of missing values. In case of fair, we hardly have very less missing values we have. Always when it comes to imputation techniques, we have to make sure that first we split our data set into training and testing. Because what happens, this is to avoid the overfitting issue. So what we do is first we split our data set into, this is the best practice, suggestive practice. We first split the data set into training and testing. We analyze the mean and median for the training data set. We find out the values for it. And then we can impute the mean and median imputation we can do for the complete data set. This is our best practice to avoid overfitting problems. Right, so let's do that. This is, we have splitted it up first. And for the training data set, we'll be analyzing the median first. This is the percentage of missing data in age and fair for the training data set. So we can see around 19% of our data in training set is missing. This is a function that I've created. So either if we want to implement a mean or a median, we can do this. And we can fill our missing values with either of them. So first we have calculated the median, which is 28 for the training data set. And for mean, it is around 30. So certainly the distribution is not normal. We can see there is a bit slight increment in mean, which we can say that there is some slight skewness observed towards the positive side of the distribution. But this is okay. This is not too much very huge distortion. This is okay. So yes, we will first replace with the median. The first thing we'll do is we will replace it with the median and then we will replace it with mean. So we added two more columns in the data frame, age after median imputation and age after mean imputation. We will compare both of them. Okay. And this is the age with the original column. First, we'll compare the variance of the feature age. That was prior to imputation and post imputation of mean and median. So this is the original variance, which is 194. After imputation, we can see the variance has reduced. But whether we go for median imputation or mean, the variance it has almost stayed the same. The variance hasn't changed a bit. So we can go for any. We can use age or we can use median also. We can go for mean also. The variance here, as you can see, is expected to give us, or we can say the reduction of variance was likely a possibility, certainly. We will see what is the reason for that in the next here. This is the plot for age. The blue line states the distribution of age before imputations. The green line is the plot of age post imputation, that is for age it is green and for median it is red. So if you compare this distribution, because the NaN values which were present in the original data set have been replaced by mean or median. So you can see that in the middle part, or where the mean or median is present, you will see there is a huge increment of the counts. So the distortions in distribution has been observed, or the original distribution has distorted a bit. So the transformed variable, it shows more values accumulated around the mean or the median data set. Why is it important? Again, as we say that there are some models, let's say linear regression, it assumes the data set to have a normal distribution. So if the distribution of the variable is getting distorted, then it may affect the performance of the model later. Right. So this is also, we have to make sure that only this technique is only applicable when we have very less amount of data missing. If we have at least, we can say at most 5% of data is missing, then we can go for mean median imputations. Not only it affects the distribution, but if we observe the outliers, or if we observe the box plot of age, we will observe that the outlier count has also increased, because the distribution has now shrinked. It has shrinked even more. So the outliers detection has increased towards the, in fact, both the ends it has increased. So we can see that after imputation, not only the distribution has got distorted, but also more outliers on the higher age values have been observed, even for lower age values also. Okay, we'll take a few questions. Okay. So next technique that we'll discuss is arbitrary value imputation. This is again for numerical data set. Arbitrary value imputation. So if we have, let's again take the same data set example with price. We have some missing values, let's say 50, 40, and then we have some missing values, and 60, 120. So arbitrary value imputation, it consists of simply replacing this missing value with an arbitrary value. Arbitrary value can be some value which is numerical in nature, certainly, but which is not a part of the distribution. Or we can say imputing either 999, either imputing 999 or either imputing -1. -1 is mostly preferred when most of the observations are positive, so we can impute it with -1 as well. Or if the variable is positive, we go for arbitrary value imputation is suitable for both. We can go for numerical and categorical. We can take both. In this case, we are only observing for numerical right now. We tend to replace the label. In categorical, we, instead of replacing it with a number, we give the category something called as a missing category. This is for categorical data set. Here we are firstly observing it for numerical data set. For categorical, we'll again discuss this again in the session later. Right. So this is the example that we have. Okay. So let's say, for example, this has some missing values. This data set has some missing values. And if we replace this arbitrary value, we can fill, in this case, let's fill it with 999. Okay. Then again, the question comes up that how to select which value to go for. For example, 99. If we want to go for 99 imputation, can we take that? It could be one of the normal values of this distribution. It could be a part of the distribution as well. So here, if you check the lower range and the upper range of the data set, it tends to go from 20 to 200, around 200, or let's say the higher range is around 120. Okay. So 99 is right somewhere in the middle of the distribution. So if this value is not certainly suitable to replace the missing data, ideally we want to look for a value that is at the end of the distribution. When we decide to use any arbitrary value imputation, we always make sure that the arbitrary value imputation is not a part of the distribution of the variable. It is present towards the extreme end of it. It can be present towards the extreme right or the left end. Here also we are making some assumptions. In this case, the main one is that the data is not missing at random. If the data is not missing at random, is one of the assumptions for this. So therefore, if we do not want to make values with missing observations, arbitrary value imputations can be done. It has also some limitations. It also distorts the original distribution. It also distorts the barriers. It distorts the covariance with the remaining values in the data set. And it also a bit distorts the interaction of that variable with the rest of the variables. If the arbitrary value is at the end of the distribution, let's say here, if we have replaced all of them, this is the value at the end, the right extreme end of the distribution, it may mask or create more outliers. And we also need to be careful not to select a value that actually belongs to the normal value range of the variable naturally. The higher the percentage of missing data, the higher the distortions, individual distortions would be. As a rough guideline, we can say that we normally use arbitrary value imputation when data is not missing at random. Another thing to remember here is that instead of using, if we are going for using trees, machine learning model related to trees, we can say decision trees, random forests. In those cases, this kind of imputation techniques works very well. It tends not to work so well with linear models because they assume that the variables are normally distributed. And here with imputations of extreme values, we are actually distorting the distribution completely. We are even adding more outliers. So this technique is not suitable for linear models, but it goes well with trees. So let's again check the Jupyter code for it. Right. We are again using the Titanic data set. We are also using the same age, fair, and survived columns. And here we have already seen age has around 20% missing and fair has very less. We will check for age column also, which has around 20% of missing data. Again, imputation important. We always make sure before imputing any missing data with something, a value or a category, we make sure that we split the data set into training and testing. We only check for imputations in training data set and we can apply it for the whole data. This is to avoid overfitting. I have created another function where in case of any missing value in the particular feature, it can be filled with a given value. So here the given value will be any arbitrary value. Let's also decide which arbitrary value to choose in both of these columns. If you see age and fair, in case of age, if you see the distribution lies from 0 to 75 approximately. So we can impute either 99 as the missing value, or we can even go for -1. We can go for both of them in age. So let's do that. So first, again, I've introduced two more columns in the data frame. The first is age imputations after 99 and age after including -1. Both the things we have, we will observe how these changes the variance and the distributions of the variable age. And we'll see and we'll compare them with the necessary visualizations. So as I said, we have taken 99 because 99 is not the part of the distribution. We can say that 99 lies towards the extreme right side of the distribution. And -1, if we talk about towards the left side of it. Okay. Again, -1 is suggested when most of the data sets are positive. We can go for -1 imputations as well. Right. Let's check for the variance, the local variance for age. So before imputation, the original variance was somewhere around 194, which has increased up to 888. A huge increment has been observed in variance after 99 imputations. And for -1, there is an observation of increment, but not to that extent as that of 99. Let's observe the plots. The blue line, if you see, indicates the distribution of age before imputation. Looks certain kind of distortions has slightly skewed, it seems, but manageable. But here in case of imputations of -1, if you see, so the green line indicates the age distribution post imputation, and there is a small aggregation of values in the -1 area of the distribution, if you see this. So this is there, I mean, the distribution has been distorted and there is a little bit aggregation observed in the -1 region. So you can see the distribution has distorted. It is no longer a normal distribution. If we observe the red colored distribution, this is for age after imputation of 99. So again, over here, if you see towards the right side, you can see some aggregation forming towards the right end of the distribution. This is due to the imputation of 99 in place of missing values. As we have discussed previously, this imputation techniques does not work well with linear models because they assume the data set has to be normally distributed. In case of trees, we can certainly go for this. This can be one of very good techniques for missing value. And however, in case of higher percentage of missing data, we always have to go for checking the impact on the distribution and also the outliers. How much is it affecting it? So let's see for outliers, how much has it affected the outliers also. So this is the box plot for age before imputation. This is after 99 imputation. We can see most of the outliers has been covered. This is certainly due to the fact that we have included 99 also in our distribution, and hence detection of outliers has reduced. Same thing has happened with -1 imputations also. So they have kind of masked the outliers. So 3 most important things to remember in this arbitrary value numerical is that first, the data should not, the missing value should not be missing at random. Second, it works well with trees algorithms and it does not really yield good results with linear models. And it highly distorts the normal distribution of the variable. Again, we have to check them always. Okay. Next technique that we will be discussing is for categorical variable imputations. These were for numerical ones. The next one we have is for categorical data type. The first one is frequent value imputation, or in simple terms, you can say mode imputations also. So we'll take another example to understand it. Let's take a variable called as brand of an automobile. So we have Ford, many number of times, and we have Fiat, BMW. Let's take Kia. Then we have a missing value. Again, we have Ford again. Then we have a missing value, and then we have Kia. So mode is nothing but the most frequent category that we have. Okay, and therefore those missing values, the missing values that we have here will be replaced by that frequent value or frequent category. Over here, if we say the mode or the frequent category would be the maximum number of occurrence of which category would this variable have, that is 4. 4 seems to be occurring majority number of times, so we can say the mode is 4. So we'll be replacing all these NaN values with mode, or that is with mode. Okay. Again, as I show, as we have discussed, that there are some assumptions for all the imputation techniques. This technique also have some assumptions. The first assumption is that the data is missing at random. Only if the data is missing at random, we can go for this. Therefore, the missing observation are most likely looked like the majority of the observations, which in this case we represent as the mode. The main advantage or the beauty of this technique is that it's very easy. It's very fast. It's fast to observe the mode of the data set, and it's very easy to implement also. And in case of when it is integrated into production, and if we want to deploy our model, in that case also, it is very easy. But here also there are some disadvantages. The first one is it certainly distorts the relationship of the relationship of the most frequent category with other variables in the dataset. And this can lead to over-presentation of most frequent categories. If there are a huge number of missing data, then there can be an over-presentation of the missing category. As always, the higher the percentage of missing data, the higher these distortions would be. So let's observe the codes and how it can be implemented, and we will also understand what the effects are. So again, in this case, we'll be using house price data set. And in that, we will observe basement quality, fireplace queue, and sale price. Okay. So we'll take these 3 columns specifically. Both these columns, basement quality and fireplace, they both are categorical features, and sales price is the target feature. So here we can see the data set, the first 5 entries of it, how it looks like. And let's also check the percentage of missing value that we have. The basement quality has around 2% of missing values, where in case of fireplace, we have around 47% missing value. We have only around 2.5 here in basement quality. So we'll replace this with mode or the most frequent category, the basement quality. And in case of fireplace also, we will replace it with mode, which is not a good practice because higher percentage of values are missing. But yet we will do it, and we will observe the distortions, how the relationship has been distorted because of this imputation. Okay. Again, one thing to look at this is that if we have higher percentage of missing values, let's say in this case fireplace, there has to be some reason that these data are missing. It cannot just be missing data at random. So we have to capture that. We also have to understand and we also have to find out the different techniques accordingly. But let's explore the missing value with mode for this. So imputation important, we have separated it into training and testing first. We will observe the basement quality, the bar plot we will observe, and we will understand which is the mode for it. So naturally, TA is the mode for the basement quality feature. The occurrence is maximum in this case. So this is the mode. The next thing is we will plot it. But here we are plotting the sales price. We are plotting the sales price for all the basement quality with mode before imputations. Okay. So this is what it looks like. If you see the blue line, this is the distribution plot for sales price where the basement quality is TA, where the basement quality is TA, or where the basement quality is the mode. And the red distribution is again the distribution for sales price for missing values, specifically for missing values. So if you check these two distributions, this is just a help for us to understand whether would it be a good practice to replace the missing values with TA or not. So if you see here, the average value of the sales price for missing values is less than that of the average value of sales price for TA. Okay, it is less. And replacing the values with TA doesn't seem to influence the distribution of the sales price overall, it seems. Let's look at it after imputation. Let's understand what the changes have happened after imputations. So let's fill it up. So we are filling the basement quality, are filling all the NaN values with Ts with the mode for both the training and the testing. And now we will explore how it has changed the bar plots, or we can say how it has changed the count of per categories. So we can see after imputation, slight increment is observed in TA. Before imputation, it was somewhere around 480, it seems. Now it has incremented a bit here in case of basement quality, because not much percentage of missing values were there in basement quality. If you see the percentage of missing value, that is only around 2.5%. So not much increment has been observed, but slightly increment is there. Okay. And this is the distribution of the original variable and the imputed variable. This is again the distribution of sales price here for before imputation and after imputation. They seem to be overlapping, it seems. The blue line seems to be not visible at all. This is because they are exactly the replica of each other. The distribution has not been affecting much. It does not have distorted a lot. And they are quite similar because the number of missing values were very less. So this can be a good practice. We can use this technique when the percentage of missing value is less. However, in case of if we have more than 5% of missing value, is this value really helpful? Let's understand that, how its impact would be. So fireplace queue is a feature which had around 46% of around 47% of data missing. So half of the data is missing. Let's understand the mode for it. So mode of this data set seems to be GD. Okay, it is one of the category and frequently occurring category of fireplace. And if you observe, around 250 is the count of it. So it has been occurring most of the times. So here, if we impute the next 50% of our data with this category, so we can assume that most of the data set for fireplace will have GD as the mode again. So it will have a huge distortions can be observed. Let's see that. So if you see again, this is pre-imputation only. The blue seems to be the sales price distribution. This is the sales price distribution of all the values where fireplace equals to GD. And the red seems to be the sales price distribution with all the NaN values. So there is a huge difference between both of these. Although the median is less than, or the average of this red graph seems to be less than the blue one, but yet there is a huge difference between both the observations already. So this is again an indicator that mode imputation in this case is not very suggestive. It will distort the sales price distribution to a very great extent. Let's observe that. So again, after implementation, we have imputed the missing values with GD for fireplace queue, and we have observed now the bar plots have also been, there are lots of distortions in bar plots also. Well, not this, these are the changes, not distortions. But in case of distributions, we will see slight distortion could be there. Previously, when we had lesser percentage of missing value, the distribution seemed to be quite normal. They were not higher in percentage, but here, if you can see, this is the distribution of sales price before imputation, and now post imputation, this is what it looks like. So it has the average house price. This is the price, right? The average house price, if you observe here, it has reduced. So this is before. So blue line average seems to be somewhere around here, and for red line, it has reduced to some extent if we have imputed the house values with mode in this case. So we can say that in cases when we have higher percentage of missing value, lots of distortions can be observed. So we have to be ready for all those challenges. These are for categorical variables, okay? So the next technique that we have is missing value imputations for categorical variables. So instead of mode imputation, we can go for we can categorize our missing values. We can categorize it into a different category called as missing category. Okay. Missing category imputation. So this method consists in treating all the missing data as an additional label. That label is missing that has been provided. They have all been treated as additional label, and the missing observations, they are grouped in a newly created label. So instead of treating it, instead of replacing it with some other value or some other category, we will create a different category of all the missing values altogether. This technique for handling missing values in categorical dataset is widely used. And to illustrate this with an example, let's say, again, we'll take the prior example. I'll just show you how it has done. So the Ford or Kia, like that, we have some missing values, a lot of missing values. And then again, we have some, and here also missing values. So these two missing values, instead of replacing it with any frequently occurring category, we will replace a category itself as missing in these places. Okay. If we want to deploy this model also, it will capture the importance of this missing value if it is actually predictive. So, and it also makes absolutely no assumptions of the data, whether it, if the data is, if the missing value is completely at random or if it's not, it has no such assumptions. You can use this missing category imputations many number of times. In case of almost all the assumptions, we can use that. Let's see the Jupyter notebook for the same. Yeah, so again, the same data set house price will take with basement quality and fireplace. We have seen that basement quality is around 2.5% missing value. Here we have around 47. Okay, so we have seen that. Again, we have splitted the data set into training and testing. And we have figured out that the basement quality has around 2.4% of missing values. And this is the mode, and this is the bar plot for it. And instead of filling it with the mode, we have filled missing value, or we can say that we have replaced the missing value with missing in both the training and the testing. So if you observe the bar chart now, you will see another category appearing here, because bar plots usually does not sense missing values or NaN values. But if you categorize them into another label, it will be quite observed. So you can see these are all the NaN values that were present in the basement quality. Now it has been labeled and they have been labeled as missing. Okay. This is a comparison of the sales price for different basement categories. So if you see, this green is for when the basement quality is something called as X. So we can say if the basement quality is X, then the sales price of the houses, or the average sales price of all the houses, is higher as compared to the others. We are more interested in this category missing. So if you see the missing category over here, the average price of the average price of the houses seems to be in the lower ranges. Okay, it is less than the higher amount. Okay. So we can say the category with basement quality X have expensive houses, but in case of our missing category, the average price is less. So our cost of houses are cheaper. or we can say the cheapest ones we have. Okay. Let's go for missing value implementation, missing category imputations for higher percentages of missing value present. So we have taken fireplace queue, and here we see that 46% of our data is missing. Okay. Again, we'll see the different categories. So we have GD, TA, FA, X, and PO for fireplace as well. And we have filled these values with missing. And we will see here, since 50% of our data was missing, so we will see the bar chart also mentioning the same category label having maximum occurrences. Because most of the data that was missing has now been labeled as missing. So we can obviously see that. Now we will compare the house prices for different labels. So over here, if you see the purple line, which is X again, for fireplace queue has most expensive houses. And the one that we are interested in is in blue. So this one, if you see the blue line, does not have really very expensive houses. They have cheaper houses. They are cheapest ones. Okay. It does not seem to have a lot of effect. We can say that the sales price has not been affected much. So we can use this technique in any kind of situations. This is a very good technique for categorical data imputations. Even for lesser percentage of missing value, even if you have half of the data missing, we can use this technique. Okay. The final topic or the final technique that we are going to discuss is random sample imputation. When we use random sample imputation, we assume that the data is missing at random. So yes, we certainly have an assumption over here that the data is missing at random. And the idea is over here, the idea of this technique is to replace the missing values with values that has the same distribution as the original variable. So randomly, it will select values from the variables, and randomly it will select those values and replace the missing values with them. So in this case, what will happen? The distribution of the variable will stays intact. It will not get distorted much. Even the outliers, if we'll see that in future, the outliers will also be handled pretty well. And we have to also pay the attention. The main feature of this is that we have to pay the attention to the randomness. Why? Because let's imagine that we have this data set with price on make of any missing observation. We replace the missing data with the random distribution of the values. So in the middle, when the model that makes the predictions are here, then we'll imagine that later, if the same model we will execute again, then another random value will be we can say implemented instead of the value that was previously implemented. So every time we will go for imputations, it will select random values, and the random values will vary every time the model is run. So for this, we have to make sure that the random value imputation follows a certain rules, and if one value is implemented, then every time the same value should be implemented, so as the model is not showing any much discrepancies in performance. Okay. Let's take this with the help of an example. Imagine, for example, that the car manufacturer is trying to predict how long a certain car will be in the garage before it passes the necessary security tests. Today, they receive a car with missing data. In some of the variables, they run the machine learning model to predict how long this car will stay in the garage, and the model replaces missing values by a random sample and then produces an estimate of the time. Tomorrow, when they run the same model on the same car, the model will randomly assign values to the missing data, which may or may not be the same value. and therefore it will estimate some other time. So every time the estimation will be different, because every time the imputation chosen will be different. It is random. So the machine learning model for each of the cases will predict different values. And because we are using random sample imputations to fit the values of some of the variables, the two cases should be identical. But here it will end up with different estimates of the time. So this may sound completely unimportant, and the businesses must follow a variety of regulations. So some of them require that the same treatment needs to be provided to the same situation. So instead of cars, there were people applying for a loan or people seeking for some kind of treatment for medical emergencies. It is needed the machine learning model always gives equal predictions, right? So this behavior needs to be controlled. So we will also see it in the Jupyter notebook, how this behavior will be controlled. You see over here, we have used Titanic dataset again. We have only taken survived, age, and fair here. And we'll see the percentage of missing value in case of age is around 20. We'll split the data set into training and testing. We will create a copy of it first, okay? So that the original column is not facing any chart, it is not distorting. So we will create a copy of it. And then we will use this dot sample method that will create or generate a random sampling of values. It will extract it from the same sample and it will impute all of the NaN values with it. Okay. And this is what we have done. So if you see the data frame, in case of age column, we have certain missing values, and then we have imputed age, the missing values with random values. These random values that have been imputed are chosen from the age column itself randomly, without any priorities. They have been chosen randomly. And this technique will also preserve our distribution, and it will also not affect the outlier distribution as well, that we will see later. And this is exactly what we want. If in case we are going for linear models, if we have even higher percentage of missing values, we can go for this technique. So if we observe the distribution of age before and after imputations, the distribution seems to have been impacted, and we see not a huge distortion has been observed because all the missing values have been treated. We can say the imputations have happened randomly. So no such aggregation has happened around the mean or any specific arbitrary values. No such aggregation will be observed. The missing values will be treated normally or randomly. In case of variance, if we observe, no slight distortions and variance is also observed. Like slight increment is there, but that is okay. So variance, local variance has also been intact. And in case of box plot also, we'll see that the outliers distribution has also remained the same only. So variance has not shrunk, variance has remained same, so outliers has also remained the same. So there are lots of advantages for this random sampling. The main criteria for random sampling usage is that we have to control the random sampling. We have to make sure that always the same value gets imputed. So this is done over here, if you see, by providing a random state. Every time when you do for random sampling imputations, we have to make sure that we provide a random state. Otherwise, every time when you run the model, it will go for random values, which will be different from the previous imputations, and it will generate different estimations. So this is a very important step in controlling the imputations. So as you see here in random value imputation is again good for any percentage of missing values. We can go for this technique. Well, we have covered up most of the techniques for missing values today. Again, as I said, these are some of the majorly used techniques. The main thing that we have to look into when it comes to any imputation technique is that first we have to look at the behavior or the method of the missing value, whether it is present at random or not at random, and accordingly, also we have to check for the percentage of the missing value. How much percentage does it have? If we are going for any technique, it is always a best practice to also observe how much distortion it has done to the normal towards the distribution of that variable. Especially in case of linear models, if we are planning to use some linear models, we have to look for distribution distortions and how it has affected the relationship between the variable and how it has impacted other variables distributions as well. If we take into consideration these steps, then we can apply techniques and it will always give you good results. That's it for today.
Hey Vaishaki, thank you so much for this informative session. I hope guys you got an idea what are the techniques which you can apply. So so basically these techniques are not a standard technique, means every time you cannot use the same technique and get a good result. It depends completely on the data. So what I would suggest you guys is to whatever Vaishaki has presented today, the various technique, try each and every technique on your data and see which and compare them, which technique performed very well. Okay, so in this way you can figure it out for this particular data set, this technique suits very well. So this is how we as a data scientist make decision on the techniques to be used. So any questions you have guys on this particular session? I have shared the code link. Okay, you can go there, download it and try to see whether means how these techniques are performing. Any question guys, you can put it in chat or on the QA section. Yes, Sapnatal, tell me what's your question. Yes, the session is recorded. Okay, you can request to care team. Okay, and you can get the recordings of the session. Okay, it is available on the request basis. And code link I have shared in the chat. Okay, you can check it out that as well. Yes, these techniques are equally useful in unsupervised technique also. Okay, any other question guys? Fine. So thank you so much for joining this session. In the next session, we will cover another feature engineering technique. So stay tuned to us. Okay. Thank you for joining, ending this session.
Thank you guys.